Lesson 7-7, Geometric Sequences as Exponential Functions, and this is day 2. Our essential question is, how do you make a table and a graph for a geometric sequence? Our first problem says make a sequence, table, graph, and equation to represent this situation. Evan paid $20,000 for his car 5 years ago. The car has depreciated in value by 7% each year. How much is his car worth now? I'm going to start out by writing an equation to represent this situation. Because we've worked with exponential growth and decay equations, and this problem says that it has depreciated in value by 7% each year. So our decay equation looks like this, because depreciated means it's going down, and so does decay. So the value that we use for A, we should be using 20,000. And R, the interest rate, is 7%, which means 7 divided by 100, or 0.07. Those are the only two values that I'm going to substitute into my equation at the start. I will eventually substitute something at the end for t to answer this question, but for purposes of making a table and a graph, I want to leave the variable t alone right now. So I'm just going to leave t in my equation. So y equals 20,000 times 1 minus 0.07 to the power of t. Or y equals 20,000 times 0.93 to the power of t. This is the equation that I'm going to use. So I'm going to put a little rectangle around it. All right. So this equation is going to help us make our table and our graph. So table and graph. Now, in my table, my variables from the equation, they're t and y. T stands for time in years, so I'm going to go with time in years. And then y is actually representing the value of the car. And that's in dollars. 0, 1, 2, and 3 are the values that I'm going to substitute in for t. So I'm using the equation, I'm using this equation right here to figure out the value of the car. So 20,000 times 0.93 to the power of 0 gives me $20,000. Next, I do 20,000 times 0.93 to the power of 1. That gives me 18,600. Next, 20,000 times 0.93 to the power of 2 gives me 17,298. I haven't had to round any of these yet. And last, 20,000 times 0.93 to the power of 3. This one I'm going to round. I'm actually just going to cut off after the decimal point, so it's $16,087. All right, now I've got my equation. So my equation is done. My table is done. Next up is my graph. So for my graph, I am going to put a little gap in because I don't really want to go up by 1,000 or 2,000 at a time when I'm talking about values from like 16 to 20,000. So I can put in a gap and then just put 16, 17, 18, 19, and 20. And 1, 1, 2, and 3 on my bottom axis. Now I need labels. It's very important that you label on your graph. So my labels, this is time in years. And then this is value of car, and I went with thousands of dollars. So I'm just going to put value and thousands in parentheses. So at time 0, the car is worth $20,000. After 1 year, it's $18,600. 2 years, $17,298. 3 years, $16,000. So here is my graph. It kind of looks like a line, but it's not. It's not. If you calculated these intervals here, it's not going down by the same amount each time, so it's nonlinear. It's nonlinear. Now, how much is the car worth now? To answer this question, let's see if we've got everything else taken care of. So we've got equation, table, graph. Oh, we need a sequence first. So let's do the sequence first. So sequence, and then we can answer the question. So for the sequence of numbers simply means taking the value of the car and writing it as a sequence. So it starts at 20,000, then it's 18,600, 17,298, 16,087, ... and so on. Okay, now to answer the question, what is the car worth now? So 7% each year, and it was 5 years ago, up there in the word problem, it says 5 years ago. So I didn't need to go all the way to 5 on my table. I can plug in 5, though, for t and solve it to get the value. So 20,000 times 0.93 to the 5th power is 13,913. This one would round up if you wanted to. So $13,914 after 5 years. So we're done with problem number 1. On to problem number 2. Make a sequence, table, graph, and equation to represent this situation again. Cottage Grove's population is currently 35,000. The annual growth rate is 3%. So now we've got a growth rate. So in our equation, I'm going to use the growth formula. So y equals our starting population times 1 plus the rate of change, and 3% is 0.03 as a decimal. Remember, you can write it as a fraction. 3% is 3 over 100. 3 divided by 100 is 0.03. And then I'm using t again for time because I need to be able to substitute different values for t to get my table and my graph. All right, so equation done. Table and graph are next. So in my table, I am going to have time in years and population so 0, 1, 2, 3 again, 35,000 for the starting population. And we said that this is growth, so this one's going to be going up. So 35,000 times, oh, I know what I need to do up here. I'm going to move something for a minute. Oops. Because on that equation, I forgot that we want our multiplier to be 1.03. So I don't want to be adding every time when I substitute this. So here is the equation that we're using. So instead of 1 plus 0.03 to put in parentheses in my calculator, it's much easier to use 1.03. Okay, so our population, so 35,000 times 1.03 to the power of 0 gives me 35,000. When I change my exponent to a 1, it gives me 36,050. When I change my exponent to a 2, 37,132. That one had a 0.5, so I just rounded it up. And when I change my exponent to 3, 38,245. All right. For my graph, I am going to put a gap in again. So graph over here. I still have 0, 1, 2, and 3 for my time, and I'm just going to go with 35, 36, 37, 38. And label, you always need labels, so this is time in years, and this is population in thousands. Okay, so times 0, 35,000, then it goes up to 36,050, 37,132, and then 38,245. Again, it kind of looks linear, but I'm going to add that little curve to it because we know that these are not going up by the same amount each time, and that's what's required for it to be linear. Okay, so we've got equation, we've got table, we've got graph. Next up is sequence. So sequence. And remember, the sequence just comes from your table. The y values, or the dependent variable, because the population depends on what year we're talking about. So here would be our sequence of numbers. And we need to answer the question in 7 years. Y equals 35,000 times our multiplier, 1.03 to the 7th power. So 35,000 times 1.03 to the power of 7 gives us a population of 43,046 people. All right, we are done with question number 2. One more example, and then you'll be ready to go. This third example is particularly important for science classes in the future because we're talking about half-life here. So approximately how much of a 12-gram sample will be left after 0.008 seconds? All right, so the half-life, I'm going to put a little rectangle around this. The half-life of a certain material is 2/1000ths of a second. And we're trying to figure out how much is going to be left after 8/1000ths of a second. And 12 grams is how much the sample starts with. Well, you need to understand the concept of half-life to do this problem. Half-life. I'm going to start out with a table and our equation, because half-life means that something is being cut in half over a certain period of time. So I'm going to put the number of half-life periods, so like how many times it's been cut in half, and the amount left, and that's going to be in grams. So the amount left and the number of half-life periods. Well, at time 0, like no half-life periods, the sample starts out with 12 grams. After one half-life period, that sample gets cut in half. Half of 12 is 6. You can divide 12 by 2 if you want to, or multiply it by 1/2. If I continue this pattern, another half-life period, then 6 divided by 2 is 3, or half of 6 is 3, and then a third half-life period would leave me with 1.5. to write this equation, y equals, half-life is like a decay. It's like decay. But the difference in the formula is that with a half-life, you know that it's being cut in half. So you can say y equals 12 times 1/2 to the power of t, like that, or the power of x. So basically, you're multiplying by 1/2 over and over and over again. So we don't need to subtract like a percentage or something like that. We can just multiply it by 1/2. 1/2 is 50%. So you could think of the rate r as 50%, like 1 minus 0.5 would give you the same equation. So we've got our table, we've got our equation. Next, I'm going to write the sequence, because the sequence we're done with. So 12, 6, 3, 1.5, ... And next would be the graph. Last would be the graph. This graph, I'm not going to put a gap in. This one's going to look really good. This one's going to look really good. So down here on the bottom, number of half-life periods. And then on the side, I'm going by 2s. The curve on this one turns out really nice because it's a higher percentage of change. So amount, so sample amount in grams, number of half-life periods, okay, it starts out at 12. After 1 half-life period, there's 6 left. After 2, there's 3 left. And after 3, there's 1.5 left. So you can definitely see the curve on this one. It's a lot more steep than the ones before. Now, the tricky part on this problem is actually answering the question, because after 0.008 seconds, or 8 thousandths of a second, how much of the sample is left? So I need to remind you that 1 half-life period is actually this many seconds long. So then 2 half-life periods, 2 of those would be 0.004, 3 of those would be 0.006. So the question was asking about 0.008. So that's actually 4 half-life periods. So you're not substituting 8 into your equation. I'm not substituting anything into my equation. I'm just looking at my table and figuring out how many half-life periods they're talking about. So if I divide 1.5 by 2, I get 0.75. So I am going to answer the question by saying after 0.008 seconds, the sample will be 0.75 grams. All right? So answering this question, here's my answer to the question right here. So answering this question, I did not use my equation. If I had wanted to use my equation, this is what I would have had to think about. This many seconds divided by how many seconds are in each half-life period, that would tell me how many half-life periods. 8 divided by 2 is 4, so that's why I just needed to go until I had 4 half-life periods. So you would be plugging in 4 for your exponent in your equation if you wanted to use the equation instead of the table to answer your question. All right, that's it for our lesson today. So you should be able to write a summary now, answering your essential question. Make sure you use complete sentences.